Here's some example problems using intensity and decibels, and also for the major section I'll give an example problem using dispersion. The peak sound level measured when a firecracker explodes, as measured by a meter 3 meters from the firecracker, is 103 decibels. What would the meter read if it had been 7 meters from the firecracker? Assumptions: okay, we're going to assume that the wave propagates away from the firecracker as a spherical wave. As such, the intensity is going to be proportional to 1 over the distance squared. Okay, so if I take the ratio of the intensity at 7 meters divided by the intensity at 3 meters, that's just going to equal then the distance at 3 meters divided by the distance at 7 meters squared, right? So basically 3 over 7 squared. So there's the ratio of the intensities, okay? So that's how much the intensity will go down by if I move from 3 meters to 7 meters away, all right? But then how do I turn that into decibels? So basically what we have is initially we have some level 103 decibels. We call this beta at 3 meters is 103 dB, all right? But that is equal to 10 times the log base 10 of the intensity 3 meters away over the threshold of hearing, all right? We want to find beta 7 meters away, all right? And that's equal to 10 times the log of the intensity 7 meters away divided by I naught, all right? But what I really have is the ratio of the two. How can I turn this into a ratio? Well, the great thing about logarithms is that when I take differences, they end up looking like ratios. So if I take beta at 7, beta at 3, the sound level at 7 meters minus the sound level at 3 meters, right? That's 10 log I7 over I naught minus 10 log I3 over I naught. All right, and then the cool thing about logarithms, well, I can factor out the 10, right? Then this is just 10 times the logarithm of I7 over I naught minus the logarithm of I3 over I naught. So the cool thing about logarithms is if you take the difference between two logarithms, it's just the logarithm of the ratio of the two things inside. So this becomes 10 times the logarithm of this divided by this. When I do that, the I naughts cancel out, and I'm just left with I7 over I3. All right? So remember, with logarithms, we add to multiply, and we subtract to divide, right? So what my reasoning was is I have an easy way to find the ratio of these intensities, and in terms of sound level, ratios become subtractions, so I subtracted the two. All right? So I want to find beta 7. All right, that's just going to be, I just add beta 3 to both sides. So the sound level at 7 meters is the sound level at 3 meters plus 10 times the logarithm of I7 over I3. All right, but that's just beta 3 plus 10 times the log base 10 of, and we had I7 over 3 is just 3/7 squared. And you can plug that into a calculator. Now, it may be a little confusing, right, because I take the sound level 3 meters away and I add something to it to get the sound level 7 meters away. You'd think the sound level would go down, right? Well, in fact, 3/7 squared is less than 1. The logarithm of something less than 1 is negative, so I actually do get something smaller. Two radios tuned to different stations individually make a sound level at your location of 78.2 and 77.3 dB, respectively. What is the sound level of them combined? Okay, now we're going to assume here, right, the reason I have to say that they're at different stations is if I have two waves that are doing the same thing, you get interference, and we'll talk about interference later. All right? And usually when we have interfering things, we add the amplitudes of the waves together. All right? So if I have two waves with an amplitude of 1, I add them, I get an amplitude of 2, and power goes to the amplitude squared, I get 4 times the power. But there's weird stuff, because if I have like waves that are the same In some places they will add together, in other places they'll be out of phase with each other and cancel out, and so we'll talk about that later when we do interference. But if I have two different radio stations, they kind of average out, right? They're sometimes adding together, sometimes subtracting, and so if you have two different sounds and you add them together, we add intensities rather than amplitude. So I'm just going to add the intensities, all right? So there's the intensity of radio 1. I'm given a sound level, right? And remember, sound level is 10 times the log base 10 of the intensity over I naught, right? So if I divide both sides by 10 and then exponentiate, I find that I over I naught is equal to 10 to the beta over 10. Or in other words, intensity is I naught times 10 to the beta over 10, right? The sound level over 10. So I1 is just going to be I naught, which is 10 to the minus 12 watts per square meter, times 10 to the 7.82, right? And I2 is just going to be I naught times 10 to the 7.73. So I've got my two intensities. I can calculate those. And then the total intensity is just I1 plus I2, right? And then my sound level is just 10 times the logarithm of my total intensity divided by I naught, which is 10 to the minus 12 watts per meter squared. All right, and then I find my sound level. All right, now, if you're in the major section and you studied dispersion, here's a problem for you, an example problem using dispersion. A wave pulse at time t equals 0 has the form y of x equals a equals that, where k naught is this. It travels in a medium with the dispersion relationship that, where beta is a constant. What are the phase and group velocities of this wave? All right, so remember the phase velocity is just, we take our dispersion relationship omega and we divide by k. If I divide this by k, that's a comma, not a prime, all right, then I get beta k squared, all right? And then, once I have my formula for my phase velocity, I plug in like the average, the typical, the average wave number for my wave, right? This isn't a pure sine wave, but its average wave number is k naught. And so I just plug in k naught. And so for this particular wave, the phase velocity is beta over k naught squared. All right? What is the group velocity? Well, for the group velocity, we take the derivative of the dispersion relationship with respect to k. So the group, we take the derivative of this. The beta comes through. This is k to the minus 1, so I'm going to get a minus 1 beta, and then the derivative of that is going to be k to the minus 2, so I'll have a k squared. All right? And then I plug in the average k for my wave, and I get the group velocity for this wave is minus beta over k naught squared. So you can see in this particular example, the phase and group velocities are in different directions. So if my wave, my pulses are traveling one direction, the ripples inside the pulse are traveling in the opposite direction, which is pretty cool.